Hello there, Mr. Sutton here, bringing you this Algebra 2 Honors 8-6 lesson on permutations and combinations. In this one, we will be finding numbers of permutations and combinations, and also applying those to find some probabilities. And as one last little thing, we are going to be figuring out the binomial theorem, which we can use to expand binomials. That will tie in with our concept of combinations. Our lesson here begins not with a definition of permutations, we'll get to that, but of a definition of the fundamental counting principle. This one says that if one event can occur in m ways and another can occur in n ways, and they could be the same or different, doesn't matter, then they can both occur in m times n ways. Basically, if you have multiple things going on, you just have to multiply the possible outcomes for each of those events, and that gives you the number of ways things could shake out if all of those events happen. And it can apply to more than just two things, but m times n is kind of the simplest case. So as a practical example of this, let's say that you have 3 pairs of pants and 8 shirts. So the number of ways that you could arrange both pairs of pants and shirts would be 3 times 8. Or 24 total outfits here. So where does this idea of permutations come into all of this? Well, a permutation is an arrangement of objects, like a pair of pants and a shirt, in which the order matters. So when we're arranging pants and shirts, you might think at first glance, well, I mean, it doesn't really matter if I pick a shirt first and then a pant. But if we just think of these as general items of clothing, then what I pick for the first item versus the second item, the order I pick those in will make a difference, because the first item is always a pair of pants and the second item is always a shirt. Another more concrete way in which order might matter is, let's say we have a race with 8 people and we have 3 people who come in the top 3. And we want to know the first, second, and third finishers in said race. So in that case, the order would make a big difference of the arrangement of those objects or those people. So if you want to write out the permutations of something, let's just take a simple case, permutations of the letter sequence A, B, C. So there is the original sequence, A, B, and C. There is also all the different sequences you could form with these letters. So you could do A and then C and then B. Again, they have the same letters, but the order is different, so that makes it a different permutation. And you could also start with the letter B and have BAC and BCA. And you could also start with C and have CAB and CBA. So in general, if you're trying to figure out the number of permutations for a situation, I mean, you could write them all out and count them up. That's one way. Another way you could do this, though, is you could figure out how many choices you have for object number 1. In this example here, we have 3 choices, A, B, or C, and then multiply that by the number of choices for object number 2. That would be, in this case, the 2 letters you didn't choose. And then multiply that by the number of choices for object number 3, the number of choices for number 4, and so on and so forth. So using our example up here, that means you would have had 3 choices initially, times 2 choices after that, times, well, there would only be 1 letter left, 1 choice. 3 times 2 times 1 would have given you 6 different permutations, which is what we see here. So with all of that in mind, here are some examples for you to try out on your own. Consider the letters in the word July. That's a great month if you're a student. We want to know, firstly, in how many ways can you arrange all of the letters, and then in how many ways can you arrange just 2 of the letters. Pause the video and try out each of these. Alright, so arranging all the letters, we've got 4 letters for our first option, times 3 letters for the next option because we used one of them up, times 2 remaining letters, times that one last letter, and this times 1 at the end is kind of silly, but we always write it just to kind of show a little respect to the 1. So 4 times 3 times 2 times 1, that's going to be 24 overall. And then if we want to just arrange 2 of the letters, we've got our first letter again, 4 options for that, times the 3 options for our second letter, and we don't need any more letters, so we're just going to stop with these 2, multiply those, and we end up with just 12 for those permutations. Now that we've learned a little bit about permutations, we're going to talk a little bit more about how to efficiently evaluate them, because some of them can get pretty big and you don't want to have to count permutations by writing out every little thing. So in order to do this, we're going to need a new mathematical operator, and let me show this to you. This is going to be an emotional moment for us. Here we go. It's this little n with the exclamation mark, which some people want to pronounce N. But we're not really shouting here. That's not what's going on. This is pronounced actually n factorial. That's what this exclamation mark is. And this factorial is giving us the product of all of the integers from 1 to whatever n is. So n factorial is going to be n times the number that's 1 less than n times the number that's 2 less than n times a whole bunch of other numbers. We just keep counting down, and eventually we get down to 3 times 2 times 1. And there, it might be a very short factorial, but this is the basic idea. You just count down and multiply. Now, just to give you kind of a concrete example, on the one of the last problems, when we were counting up the number of ways of arranging the letters of July, that was 4 times 3 times 2 times 1. We could have written that as 4 factorial. So this would have been kind of how you find the permutations from that situation. And this again would give us 24. So we can see right away, just based off of this in our last example, how this factorial operator might be kind of helpful for figuring out permutations. Let's talk about a shorthand for asking for permutations now. So when you see something in this format, NPR, so a number, a big P, and another number, and those numbers are both little subscripts, this is just saying the number of R length permutations from n items. For example, when we asked for how many 2-letter permutations can we make from the word July, we were asking for 4 P2 in that situation. So let's talk about how to evaluate things that are in this format. Let's start with a few base cases that we don't really need anything fancy for. We can just kind of reason them out. So let's start with NP0. And n can be any number that we want. But now keep in mind that n and r are going to be positive integers, or they might be 0, so whole numbers in other words. So this is asking right now for the number of ways to arrange a 0 length sequence of n items, whatever they are. Well, how many ways can I arrange nothing? There's only one way, and that's just to not arrange anything at all. So this is a weird case, but it actually is just 1, which is kind of odd. We can't really think about it as like taking 0 and the number less than 0 and all that. It's just sort of a base case that we can't really explain any further than what we have. Now let's take another interesting case. Let's say I do NP1. This is the number of ways of taking one object from a list of n objects and arranging them. Well, any of those objects I take, there's only one way to arrange n of these, but there's n of them, so there's actually n different ways to do that. You just take a different of the n objects every single time. So if you see some number, P1, it's just whatever that first number was is your answer. So these are good to know. These are kind of common cases that you might see. Now what if you have NP something that's not 0 or 1? So there's a general formula for handling every situation, and it actually does work on these as well. Here's the general formula for NPR. So if you just had NP1, then you would just need n, right? But let's say you had NPN. So that would be how many ways to arrange all the items. And we saw that when we were arranging the letters in July up here, we needed to take the total number of letters and take the factorial of that total number. So for NPR, we start with the idea of just taking the factorial of however many items are in the list, so n factorial. But we might not want all of those arrangements. When we just wanted all the 2-letter arrangements of the word July, we didn't really need this 2 times 1 piece of it. So to get this r in here, if it's anything other than n, we also need to do n minus r and take the factorial of that and divide by that. So n factorial over n minus r factorial. So do the subtraction first, then the factorial. That's going to give us the total number of permutations. So we're going to give you a chance to give this a test drive now. We could actually give it a test drive right up here just to make sure it works. So recall from the last example that when I just took the first two letters of the July arrangements, I got 12. So here we would have 24 divided by 2 factorial would just be 2. So 24 over 2 would have given us 12. This formula does work on that little July example. Here's some more examples for you to play with. So I'm going to give you 2 of these. This first example, 5p2, I want you to try that using no calculator whatsoever, just your knowledge of factorials and this formula and what it all means. For the next one, example B, 7p3, you are allowed to use the factorial operator on your Desmos calculator for that one if you want. So pause the video and give these both a shot. Alright, so if I'm doing 5p2, that means I'm going to have a 5 factorial in my numerator and 5 minus 2 in parentheses factorial down there. Now I could just fully expand this and multiply the numerator, multiply the denominator, and then divide, but that actually might be a lot of work and might be something I need a calculator for. A more clever way to do this is you can actually partially expand factorials. This 5 factorial, for example, I could call this 5 times 4 times 3 factorial. I can stop expanding at any point that I want. Now, why would I do this? Well, this denominator is actually itself 3 factorial. What can I do with these 3 factorials? You got it. I can cancel those because these are really both 3 times 2 times 1s, which would cancel anyway. So that means I just have 5 times 4 up here, which is just 20. So that's a way you can do a lot of these without a calculator. And you might not be able to cancel every little thing in the denominator, but you can at least break it down a bit so that it makes your life easier. Now let's do this next one, and we'll use the calculator after we set this up. So we would have 7 factorial over 7 minus 3 factorial. And now if I'm going to go ahead and do this on the calculator, let me make a fraction. Let me do 7 and then just exclamation mark. It is that easy. Divided by parentheses 7 minus 3 factorial. And that's just 210. Which we could have found doing it by hand, but it's nice to have a calculator option. Now there is even a fancier way to do this on the calculator, which you're not going to be allowed to use on your homework for this part of it. I want you to get practice using this permutation formula here. But if you're just trying to find, for example, 7p3 without even writing any of this out, you can, on Desmos, on the scientific version of Desmos even, use the NPR function. You just type NPR, and I think you need the uppercase P, and then a parentheses, and then your N, comma, your R, close the parentheses. So for this one, let's go ahead and try it out. So NPR, parentheses, and then we have a 7 for N, comma, 3 for R, and it gives us 210 just like we got doing the other way. Our next topic is going to be something that gets confused with permutations quite a lot, called combinations. A combination, like a permutation, is an arrangement of objects. The difference here is that with a combination, this arrangement of objects has an order that does not matter. So, for example, let's say that I have 3 randomly chosen pizza toppings out of 12 or however many. So, for most people, if you randomly pick 3 pizza toppings, it doesn't matter to you the order that you pick them in. You're not telling the people who are making your pizza, okay, first put down the pepperoni, then put the onions on top of that. I mean, maybe some people are that, precise in their pizza construction, but most people aren't. So as an example, using some letters here, let's say that we want the different combinations of A, B, C. Well, how could I arrange ABC? We have ABC. That's one way to do it. We could arrange it as ACB, but the order doesn't matter. So that actually wouldn't count as a different combination. It's the same letters, so it would not be a different one. By the same token, if I wrote BAC or BCA or anything with a C in the beginning, none of these would count as different combinations. Other orders are not new combinations. To have a different combination, you actually need to have different items in the arrangement. So that's a bit of a game changer. As you might imagine, typically you're going to have far fewer combinations than you have permutations. So for this next example here that you're going to try out in a minute, I'm going to have you list out and count the possible combinations of two letters chosen from the list A, B, C, D. Now, one reason we do permutations before combinations is because the combinations are actually part of the set of the permutations. To figure out the combinations, if you're writing stuff out, you can actually just write out all the permutations and then just cross out the ones that have the same combinations, that have the same exact letters in them. So with that in mind, pause the video and see if you can figure out how many combinations we have from this list of letters. Alright, so let's write out all the different permutations with two letters first. So we'll do all the ones that begin with an A first. So AB, AC, and AD. And then we'll do all the ones beginning with B. So BA, BC, BD. And next the C's, CA, CB, CD. And finally the D's, DA, DB, and DC. Now let's go through and see how many actually have different sets of letters. So we'll just go down each column from left to right. So AB, AC, AD, those are all unique. BA is actually not different from AB. It's the same combination, the same letters in it. So we'll cross that one off. BC is different. We didn't see those together before. BD is different from all the ones we've seen. Next column, CA, that's the same as AC. CB is the same as BC. CD is different. We've never seen a C and a D together before. And now for our last column, DA is the same as AD. DB is the same as BD. And DC is the same as CD. So we'll cross that one off. So just counting these up, 1, 2, 3, 4, 5, 6 different combinations that are actually unique. So just like with permutations, combinations have a shorthand notation. NCR, or sometimes people call it N choose R, is the number of R-length combinations from a list of N items. So on the last example we saw where we were figuring out two-letter combinations of A, B, C, and D, that would have been 4 choose 2. Now just like permutations, there's some base cases and a formula for figuring out combinations to save us a little bit of time. Let's start with our base cases. So let's start with NC0. This is the number of ways of choosing 0 items from a list of N. Well, there's again only one way to do that, just like with the permutations, and that's to choose nothing at all. Now, how about N choose 1? This is the number of ways of choosing 1 item from that list. And this is just like the permutations, because the order mattering or not mattering doesn't really matter if there's only 1 item on the list. You have N of these, you pick a different one for each of your different possibilities, so there's going to be N total for those combinations. Now there are a few other base cases for combinations because the order doesn't matter. We get some special situations. Let's, for example, take the case where we have N choose N minus 1, where the R is actually 1 less than the N. So for example, like 8 choose 7. In this situation, you're basically leaving 1 item out each time, and it doesn't really matter what order the other 7 or however many items are in. So this is, you could think of this as the number of ways to leave out 1 item, which is just going to be N again, because there's N different items that you could exclude rather than include. And the last crazy situation is if you have N choose N. This is if you're picking every single item on your list. Now, because the order doesn't matter, if you choose every item on your list, that's kind of all you can do. You could switch the order, but it's not going to give you a different combination. So there's actually only one combination if you use all the items in your list. So there is a formula that we're going to see in a moment, but again, it's good to know these base cases, because if you see one of these, you can save yourself a lot of work just reasoning it out. But let's look at that formula. So like the permutation formula, we're going to have a numerator with n factorial in it. First we need to figure out like all the different ways of arranging every single item if it was on the list. And just like the permutations, we're going to divide by n minus r factorial. But there is one little difference, because in addition to excluding these ones, we also want to chop out all the repeats. So we need to basically figure out all the different permutations of r that we don't care about and divide those away as well. So this denominator needs an r factorial as well as an n minus r factorial. Now just to prove that this actually works, our last situation where we're picking two letter combinations of that four-letter list A, B, C, D, where we were doing 4, choose 2, let's use this formula and see if it actually works. So here I am on Desmos. Let me do a little fraction here. Let me do 4 factorial, and let's divide that by 4 minus the r value 2 factorial. And then the r value was 2, so we'll do 2 factorial. And it looks like that's all coming out to 6, just like we got when we wrote out all the different combinations and counted them. Alright, so we know this formula works. We'll use it when we have to. Here are 2 examples for you to evaluate. Just like we did with permutations, this first one, I'd like you to try this without a calculator, just so you know your way around and that you can do it. And then you can use the factorial on the calculator for example B. Give it a try. Alright, so let's use our formula for part A. So we're going to have 8 factorial over 8 minus 6 factorial times the r value 6 factorial. And again, if I have to do this being a little bit clever without using a calculator, I can do a partial expansion of any of my factorials. This 8 factorial, I think it would be helpful to split this up into 8 times 7 times 6 factorial, because I've got this 6 factorial down here. I'm going to write that 6 factorial first in the denominator. I guess it doesn't really matter. And then this 8 minus 6 factorial, that's really 2 factorial. I can write that as 2 times 1 if I like. So let me do some reducing now. These 6 factorials cancel out, which is very nice. And then the 8 and the 2 can also reduce to give me a 4 up here. So when the dust settles, 4 times 7 gives me 28. So again, if you're a little bit sneaky about it, you don't need a calculator for a lot of these. Now let's look at this next one. Breaking this up using our formula, we've got 11 factorial over 11 minus 4 factorial times 4 factorial. And we'll just go full calculator on this one. So on the calculator, we've got a fraction, 11 factorial, which if you just took a look at it would be a very large number. And then down there we have 11 minus 4 parentheses factorial times, so by the way, this is the number of permutations if we did 11p4, but now if we throw in this extra little 4 factorial to get rid of all those repeat permutations, that breaks our number down to just 330 different combinations. Just like with permutations, there is a Desmos shortcut for doing this. So to do this on Desmos without breaking it down with the formula, you can use n capital CR and then in parentheses do your n comma r. So just to show you that one, just to show you that it works, n capital CR parentheses 11 comma 4 gives us 330, just like doing it the slightly longer way. So this concludes part 1 of this lesson on permutations and combinations. In part 2, we're going to be figuring out how to use these in a few practical application situations, and we will also be using our combinations to drive something called the binomial theorem. Stay tuned. Welcome back for part 2 of this lesson on permutations and combinations. In this one, we're going to do a little more practical application now that we've got sort of the nuts and bolts and a few Desmos shortcuts for using them. So for this page here, we're going to talk about applications of these things when we're just counting numbers of things. So our first example here, you order a sandwich at a restaurant. You can choose 2 side dishes from a list of 8. How many combinations of side dishes are possible? So this is a typical permutation or combination situation when you're choosing a certain number of items from a bigger list of them. So the key on all of these counting kind of situations is going to be to figure out whether the order matters, and then based on that use either NPR or NCR on the Desmos calculator if you want. So pause the video and try out example 5. Alright, so since I'm ordering 2 side dishes, the order that I order the side dishes in doesn't really matter. It's not going to change the construction of the meal. So since order doesn't matter, we're going to use a combination on this one. I have 8 total items and I'm choosing 2. So if I just do 8 choose 2, 8C2 on the calculator, that'll give me the number of combinations of side dishes. Let's go to Desmos then. So let's clear all this out. Let's do NCR, and then that would be 8, 2, which gives us 28 different combinations of side dishes. For our next example, we have 10 horses running in a race. We want to know in how many different ways can the horses finish first, second, and third. And again, we're going to assume that there's no ties in this situation. Pause the video, try this one out. Alright, so we're counting different ways to arrange our horses, and because we have a first, second, and third going on here, it makes a very big difference what order those horses are arranged in. So order matters here. So that means that we need to use the permutation formula. So this is going to be 10p, and then there's 3 that we're arranging, so 10p3, and we will go to the calculator for that. So let me do NPR, and then we'll do 10, 3 in there, and that gives us 720 different ways to arrange those horses. For this next set of problems, we have an element of probability being involved. This next example here, you ride on a float with your soccer team in a parade. There's 12 floats in the parade, and their order is chosen at random. We want the probability that your float is first, and the float with the school chorus is second. So we're asking for a probability at this point. Now remember, with probability, we want basically number of favorable outcomes divided by total number of possible outcomes. And where the permutations and combinations can help us out here is we can use those things to find the total possible outcomes. And then we'll just need to think a little bit about how many of those are favorable outcomes. So with that in mind, in this situation, again, figure out whether the order matters or not. Pause the video and use some of what we've learned. So because we want our float to be first and the school chorus to be second, we don't just want to be in the first 2, we want to be number 1. The order matters here, so we're going to need a permutation. There's 12 items in the list, and we're picking 2 of them, so we need 12p2 permutation here. Let's figure that out on Desmos. So we've got NPR and then 12, 2. So there's 132 different orders that we could have for those first 2 floats. Now only one of those has us first and the school chorus second. So that means that we're going to be doing, for our probability, 1 over 132, probability of soccer first and chorus second. For this next one here, we have a yearbook editor selecting 14 photos, including one of you and your friend to use in a collage. The photos are placed at random, and there's room for 2 photos at the top of the page. Everyone wants to be at the top, right? We want to know the probability that your photo and your friend's photo are the 2 placed at the top. So pause the video and see what you can do with this one. Now, in this situation, because we don't care which order the your photo and your friend's photo go in, the order does not actually matter in this case. So we can use a combination. We have 14 total photos and we're picking 2 of them. So we need 14 choose 2, which again we will do on our calculator. So NCR and then 14 comma 2 gives us 91. And out of the 91 different combinations, there's only one combination that has you and your friend together. So that means that we're going to have 1 out of 91 for the probability that you and your friend are at the top of that collage. The next cool thing we're going to be doing with combinations is something called the binomial theorem. So take a look at this problem here. They're saying use the binomial theorem to write the expansion. And we've got 2x plus y squared, all of that raised to the 4th power. Now we already could do this using, you might remember, something called Pascal's triangle, where you write down your triangle of numbers, and every number was the sum of the 2 numbers above it, and you had ones going down the sides, and you'd have to take this down 4 levels in order to figure out the magic coefficients that went with your A and your B. So you might have wondered, well, what if I have something that is obnoxiously large? Like, let's say it's not 4th power, let's say 10th power. Is there a shortcut to figure out all those magic Pascal triangle numbers without actually building the full triangle? It turns out that there is, using combinations. So enter the binomial theorem. The binomial theorem says that in the expansion of a plus b to the nth power, each term from r equals 0 to r equals n, where 0 is your first term and n is your last term of this expansion, each term will be of the following format. The magic Pascal triangle number is just going to be NCR. Whatever level you're at in the triangle, combination, choosing whatever item, whatever term number that you're trying to figure out there. So for example, if you wanted to go down 3 levels and get the first item, we would do 3 choose 0. And I actually just want to show you this briefly on the calculator just to kind of prove that this does the same thing as Pascal's triangle. So if we did NCR and then 3 choose 0, that would give us 1. And I mean, that shouldn't surprise us because there's only one way of choosing 0 of 3 items. If we did 3 choose 1, that would be 3. 3 choose 2 would be 3. And 3 choose 3 would be 0. And you might remember from Pascal's triangle, 1, 3, 3, 1, that was your 3rd row of Pascal's triangle. So this gives you all those numbers in those rows, which is pretty nice now that you know how to use combinations. To go along with this, we also have the things in the actual parentheses. So that A, what's happening with that A? Well, that's going to be A to the n minus r. So you have your highest exponent first because you're doing the highest exponent minus the 0 because this is the 0th term. Then you'll have B to the rth power. And this handy little formula will give you any term you want of any level of expansion. It'll give you only one term at a time, but maybe that's all you need. Or you can use it to expand an entire binomial, as we're going to do in this example down here. So let's use the binomial theorem here. We're going to do the first couple of these together. So if we're doing our first term is going to be, since we have a 4th power here, we're going to have 4 choose 0 for that first coefficient. And then A is really this 2x here. So we've got 2x raised to the 4 minus 0, which is just 4. B is just the y squared. So we've got y squared raised to the r power, which is 0 in this case. So this will be our first term once we simplify it. Then for the next term, well, we've got, this will now be, we still have 4, but we're going to be using the r value 1 because we're on to the next term. So this will be 4 choose 1. Now we've got 2x to the 3rd power. and y squared to the first power. So just like Pascal's triangle, as one exponent goes down on the a, the other exponent goes up on the b until you're back to that n value. So pause the video and see if you can go the rest of the way. I would recommend writing out the rest of your binomial theorem type terms here and then simplify everything. Give it a shot. Alright, so for the next one, we're going to have 4 choose 2, our value of 2 for this next one. 2x to the second, and then y squared to the second. After that, and I'm going to continue on the next line because I'm running out of space, we'll do 4 choose 3. 2x to the, we're going down by 1, so 2x to the 1, y squared to the 3, and then finally we've got 4 choose 4. Now we've got 2x to the 0 and y squared to the 4th. Let's go back and simplify all these. 4 choose 0, anything choose 0 is 1. 2x to the 4th power, that's going to be 16x to the 4th. Y squared to the 0, anything to the 0 power is 1. Moving on to the next one. 4 choose 1. Remember, when you have a 1 here, you just use the n value, so that's just going to be 4. 2x cubed, that's 8x to the 3rd power. And y squared to the 1 is just y squared. On to the next. 4 choose 2. Well, let me go to Desmos for those. So let me just piggyback off of this earlier choose that I had plugged in there. We're doing 4 choose 2, and that gives us 6. So that would be 6. And then we have 2x squared, so that's going to be 4x squared. And then y squared squared, we multiply the exponents, so that's y to the 4th. On to the next, we have 4 choose 3. Remember, when we have n choose n minus 1, we just have n ways of doing that. So that would just be 4 again. But you could have plugged it in the calculator if you wanted. 2x to the 1st is just 2x. Y squared cubed, that's going to be y to the 2 times 3, y to the 6. And then finally for this last one, 4 choose 4. There's only one way of just taking all the things in our list. 2x to the 0 is just 1. And y squared to the 4th, that's going to be y to the 8th. We'll do our final round of simplifying now. This just does take a while, but it's still a lot faster than Pascal's triangle or writing 4 of these and multiplying it out the long way. So back in the beginning, this is just 16x to the 4th. Here we have 32x cubed y squared. Next, this is 24x squared y to the 4th. After that, this is 8x y to the 6th. And finally, this is just y to the 8th. So at this point, now that you've seen binomial theorem, some of you are like, hey, that's pretty cool. And some of you might be like, hey, that's pretty cool, but it doesn't really save me that much more time than Pascal's triangle, which I'm already familiar with. And that is totally fair if you're expanding the whole binomial and you're not going to a super crazy exponent. But what if, like in this situation, you want just the coefficient of one of the terms of an expansion, in this case x to the p-value 4, so x to the 4th, and let's say that you have a crazy big exponent like 10, or even something more obnoxious than this. I mean, if you're game for 10 levels of Pascal's triangle, I'll just make this 20 or 30. I mean, I can keep going pretty easily. So at some point, we are going to need the binomial theorem to do this efficiently. So situations like this, it's actually pretty quick business. And again, here's the binomial theorem, the relevant piece of it. It's actually pretty quick business to just plug your a, b, n, and r into this theorem and simplify it to get you that coefficient that they're looking for. The only thing that's a little bit tricky on this, a, b, and n are pretty easy to pick out of this, but you might be wondering, well, what's the r value that I would use in the binomial theorem? So the r value, that's essentially how many terms away you are from the very first term. The very first term we call r equals 0. After that, it's r1, r2, r3, all of those. Now, the way that this works is I'm looking for x to the 4th, but I'm starting with x to the 10th, something with x to the 10th in it, and I'm counting down. So to get this r value, I need to subtract this p-value from the highest exponent, from the n value. So r if, assuming that we have x to the first power, if it's something x to some other power, then all bets are off. But if it's just x to the first power, then your r value is just going to be n minus the p-value. So with that in mind, pause the video and see if you can figure out the coefficient of this thing, x to the fourth, using your binomial theorem. Alright, so let's first figure out our n and our r value. N is just the 10 up here. R is going to again be n minus p, so 10 minus 4, which is 6. So I am going to have 10 choose 6, and then my a value is 3x. So that's 3x to the n minus r, which 10 minus 4 is going to be 4, or 10 minus 6 rather is going to be 4. And then we're also going to have my b value, which is just 2. So we're going to have 2 to the r value of 6. And then let's just evaluate all this. Let me use the calculator for 10 choose 6. So let's do NCR, 10 choose 6, and that's 210. Glad I didn't have to do that by hand. So we've got 210, and then this is going to be 3 to the fourth and x to the fourth, so that's 81 x to the fourth. And then finally 2 to the sixths I know is going to be 64. We need to simplify this a little bit more to find out the coefficient. It's important to note that this 10 choose 6 doesn't necessarily give us the coefficient. It wouldn't unless this was like 1x to something and this was just a 1 over here. Typically there's other coefficients involved, so we really have to fully simplify this to get the overall coefficient. So let's do 210 times 81 times 64. And that is going to be 1,088,640, and then an x to the fourth, which means that our coefficient is just the number part of that, 1,088,640.